I had a question concerning an example problem from the books. This is example 2910. And in this example problem, there's a capacitor. Now, the important thing here is that this capacitor is hooked up to a battery. Okay, so it's connected to a battery and it stays connected. And so there's some potential difference for the capacitor. We'll call it delta V0. There's some separation of the plates D. And then there's some electric field, which we can write as delta V0 divided by D. And then there's the capacitance of the capacitor, which is just epsilon naught A over D. And what they do is they fill this up with a dielectric, so K constant K, or kappa. And so what that means is, so notice all these values here with the 0 are the values before we put in the Mylar strip. And so once you put in the Mylar strip, the new capacitance will be kappa epsilon naught A divided by D, which is just kappa times C naught. So by putting in the strip, you've increased the capacitance. Now what does this do? Well, there was a charge Q0 on there. When you put in the Mylar strip, you're going to increase that charge. And so what happens is here, when you have it connected to a battery and it stays connected, the voltage stays the same and the electric field stays the same. And so then the problem calculates the energy as so. And so what it does here is it says, okay, so my capacitor has increased by kappa. So if I plug in for my capacitance, it's kappa epsilon naught A over D. Now the potential, they like to put that in terms of the electric field, but again, in this case, it hasn't changed because it was staying connected to the capacitor. So if I do this and do all the little algebra here, I get kappa epsilon naught area times the separation of the distance, and then the electric field, which is the same electric field, it hasn't changed. And so then what the book does is it divides this by area times distance to get what they call the energy density. And so when I cancel out, in this case, the A and the D, I get the energy density as just being like this here. And so what's happened is in this case, so if you look at these two pieces here, when I put in the Mylar strip, the capacitor increased, the potential stayed the same, so overall, the energy density increased by one factor of kappa. Now, an alternate way that you could do this problem would be to take the capacitor, charge it up to some voltage with the battery, and also some electric field, the same sort of idea. So it's the same kind of picture, okay, with the distance of separation. But here, when it charges up to Q0, you separate it from the battery, so the charge stays the same. So when that happens, when I put in the Mylar strip with kappa K, okay, so just like last time, this guy, the capacitance will increase. However, in this case, both the new electric field and the new potential difference, be careful here, electric field will be the old electric field divided by kappa, so that's decreased. The new potential difference, by the same token, will decrease by a factor of kappa. And so we can write the potential, the new potential, as E0D divided by kappa. So because the charge stays the same, okay, in the last problem the battery allowed the charge to change, but here it has to stay the same, so the electric field decreases. And so if I do the same calculation of the energy here, okay, so what's happening is the capacitance will increase, the potential will decrease, but since the potential is squared, it's more important. So basically, the equation that the book gave for the energy density is not does not work for every instance. So you've got to look at every instance in particular. And so here, if I plug in my values, I get K epsilon naught A over D. And then if I plug in for here, the electric field, so I'm going to plug in this right here into there. And so I get E0 D squared over kappa squared. The result that I get is a 1 over kappa. Epsilon naught A D, the electric field squared that we started with. And then if I do the same thing, divide this by AD to get the energy density, so I'll get 1 over 2 kappa. So again, that equation that we had there, that they use in that example is not a equation that works for every example. You've got to kind of look at these situations and see what is in fact staying the same.